Okay, thank you. Good morning to all of you. I am Rama Krishna from Care University, delivering the series of lectures on heat transfer. Today's topic is radiation exchange between surfaces. In the last class we have seen the fundamentals of radiation. Of course, a little bit hurriedly we have finished it because most of the students might have finished that part at their intermediate level itself. However, this is the most important session for an engineer to determine the radiation exchange between different bodies. Though the radiation exchange occurs between different bodies that exist surrounding us, we majorly concentrate on radiation heat exchange between two bodies. And of course, in certain cases with a third body also. When more than three bodies are involved in radiation exchange, as we are going to see, the problem becomes more difficult to solve in a classroom, and hence we are not going to discuss that part in this session. Anyhow, at the end of this session, the student is able to understand what is a shape factor or U factor or a configuration factor, and how to determine the shape factor, and what is shape resistance and surface resistance in the radiation heat transfer problems, and how to apply electrical analogy to solve radiation problems. Imagine there is a point source which is surrounded by three surfaces as shown here, surface 1, surface 2 and surface 3. The energy emitted from this point source will go and fall on all the three surfaces, and the radiation heat transfer between these surfaces depends on the orientation of the surface. For example, if you see here, the surface 2 is vertical, it receives minimum amount of heat from the point source, whereas the surface receives maximum surface 1 a little more or a little less than surface 3 more than 2. So the radiation heat transfer between the surfaces depends on the orientation of the surface relative to each other, as well as their radiation properties and temperatures. Like radiation properties, its emissivity, absorptivity, transmittivity, and of course its temperature also. This depends on the orientation is accounted for by a term called U factor or configuration factor. For example, if you face the fire from front or back, you receive maximum radiation. Instead, if you are facing the fire from the side, you receive minimum radiation. Now let us go to the U factor or shape factor or configuration factor or angle factor. Suppose there is an area, a body with an area dA1 and another body with area dA2. Both bodies emit energy continuously in all the possible directions, this A1 and A2. But the total amount of energy emitted by a body A1 is in all 360 degrees angle or in all the possible directions, and the amount of energy emitted by this body will not go and fall on body 2. Only a fraction of the energy emitted by this body will go and fall on body 2. Similarly, this body 2 will also emit energy in all possible directions. Out of the total amount of energy emitted by this body 2, only a fraction of amount of energy will come and fall on body 1. That fraction of energy leaving a surface I and that strikes the surface J directly is known as shape factor F I to J or U factor F I to J. If I write F1 to 2, it reflects that the fraction of radiation leaving surface 1 and received by the surface 2. If I write F2 to 1, it is the fraction of an amount of energy leaving body 2 and received by body 1. So F1 to 2 is shape factor between 1 and 2. F2 to 1, shape factor between 2 to 1. It is also called angle factor or configuration factor or U factor. How to determine the fraction of energy leaving a body 1 and falling on body 2? Let us consider a geometry like this, where you have a body A1 and another body A2. In the body A1, take an area dA1 making an angle θ1 with the normal, and another area dA2 here, the normal of it is making an angle θ2. The steradian angle that is covering the radiation from dA1 to dA2 is, let us say, d omega 2 to 1. The same figure is reproduced here. You assume that the distance from dA1 to dA2 is r. The angle between the normals n1 and n2 that connects dA1 and dA2 are as shown here, θ1 and θ2. This surface dA1 emits and reflects radiation diffusively in all directions with a constant intensity of I1, and solid angle subtended by dA2 when U'd by dA1 is, say, d omega 2 to 1. Now, as we have seen in the fundamentals, the rate at which the radiation leaves dA1 in the direction θ1 is I1 cos θ1 into dA1. Reference to this I1 cos θ1 dA1, the steradian angle dWt1 is equal to dA2 cos θ2 by r square. So Q dA1 to dA2 is IA1 cos θ1 dA1 into d omega 2 1, which is also equal to IA1 cos θ1 dA1, and in the place of d omega t1 we will write dA2 cos θ2 by r square. The total rate at which the radiation leaves dA1 in all directions is called its radiosity, that is pi times the black body intensity, or J1 is pi I1, the surface times the surface area. So Q from that elemental area dA1 can be written as J1 dA1, which is also equal to pi I1 dA1. Differential U factor dF dA1 to dA2, which means the energy leaving dA1 and received by dA2 directly is given by dA1 to dA2 by Q dA1, that is I1 cos θ1 dA1 into the steradian angle dA2 cos θ2 by r square by pi I1 dA1. So which gives cos θ1 cos θ2 by pi r square dA2. The U factor from a differential area dA1 to finite area A2 can be determined from the fact that the fraction of radiation leaving dA1 that strikes A2 is the sum of the fractions of radiation striking differential areas dA2. Therefore, f of dA1 to dA2 is determined by integrating df dA1 dA2 over A2. So f of dA1 dA2 is by integrating this df dA1 dA2 over an area A2 cos theta 1 cos theta 2 by pi r square dA2. That will give the total rate we have seen already as pi IA1 A1, and QA1 dA2 is integral of Q dA1 to dA2 is I1 cos theta 1 cos theta 2 by r square dA1 d2, and integration of this is again between the limits A1 to A2 gives the radiation that strikes the entire area Q A1 to A2 as double integral of A1 to A2 I1 cos theta 1 cos theta 2 by r square dA1 d2. So we know that f of A1 A2 is nothing but Q A1 A2 by Q A1, which is equal to 1 by A1 times integral A1 A2 cos theta 1 by cos theta 2 r square pi r square into dA1 dA2. Or in other words, f of 2 to 1 instead of 1 to 2, you can write f of 2 to 1 as Q A2 to A1 by QA2, which is equal to 1 by A2 double integral A1 A2 cos theta 1 cos theta 2 by pi r square dA1 dA2. These relations confirm that the U factor between two surfaces depends on their relative orientations and distance between them. The relative orientations are through these angles theta 1 theta 2, and the distance is r. So as the distance increases, the shape factor goes on decreases. So from these two equations, if you carefully see, Q dot A1 A2 is F122 A1, we can see, and Q A2 A1 is F221 A2. So if there is a possibility for developing a relationship between the shape factor and the area, and that kind of rule which we are going to develop is called the reciprocity rule or reciprocity theorem. In simple terms, let us assume the amount of energy leaving a body 1 whose temperature is at T1 and falling on 2 is sigma A1 T1 power 4 into shape factor F122. What is F122? F122 is the amount of energy leaving the body 1 and falling on body 2. So if you multiply the amount of energy emitted by 1 with the shape factor F122, you will get the amount of energy leaving 1 and falling on 2 as sigma A1 T1 to the power 4 into F122. Similarly, the amount of energy falling on 1 out of energy emitted by 2, Q221 is sigma A2 T to the power 4 into F221. So net heat exchange between the two phases is Q122 can be written as sigma A1 F122 T1 to the power 4 sigma A2 F221 T to the power 4. When both surfaces are at same temperature, there will be no net heat exchange. So when T1 equal to T2, this Q12 will become 0. Therefore, you will get sigma sigma cancels, T1 T2 cancels. You will get A1 F122 is equal to A2 F221. This A1 F122 is equal to A2 F221 is known as the reciprocity relation, because if the area is more, the shape factor will be less. Area is less, the shape factor will be more. So it is a reciprocity relation. The U factor relations developed above are applicable to any two surfaces, I and J, provided that the surfaces are diffuse emitters and diffuse reflectors, so that the constant intensity condition is valid. Let us consider a plane surface like this. It continuously emits energy in all directions. no energy emitted by this will come and fall on this. So therefore, the shape factor F with reference to surface 1 to itself is 0. Consider a convex surface like this. Shape, the amount of energy emitted by this goes in all directions and none of this energy will come and fall back on this. So F222 is equal to 0. Now consider a concave surface like this. Some of the energy emitted by this concave surface can come and fall on itself. Therefore, F323, some part will be there falling again on it, hence it is not equal to 0. Now imagine a sphere like this. One solid inner sphere is kept in a hollow outer sphere. So the energy emitted by this inner sphere ultimately has to come and fall on the outer sphere too. So therefore, the total energy emitted by inner sphere has to be received by the outer sphere, hence F122 is equal to 1. So that consists of these two concentric spheres. The entire energy leaving the surface of smaller sphere will be intercepted by the larger sphere, hence F122 is equal to 1. So because it is not possible to have this kind of imagination with reference to other geometries, relations are developed based on the orientation of the surfaces as well as the size and the distance between them as the shape factors. Aligned parallel rectangles, if you have, the shape factor Fi to j is given by this expression. If you have coaxial parallel discs, one I and let us say other one j, separated by a distance L, you have shape factor Fi to j using, you can determine using that formula. If you have perpendicular rectangles with a common edge, that is they are touching together, 90 degrees they are making between the planes with y, z, x dimensions as shown here, then shape factor you can determine using this formula. If parallel plates with midlines connected by a perpendicular line, then formula for shape factor is this. If you have an inclined plate of equal width and with a common edge as shown here with an angle alpha in between the two plates, then Fi to j is given by this formula. If you have perpendicular plates with the common edge, again this is the formula. If there is a three-sided enclosure with different dimensions ijk, f of I to j is given by this formula. And for infinitely long geometries, if you take like this, a cylinder separated by a distance s, then f of I to j is given by this formula. So with reference to all these things, we can finally conclude that the reciprocity theorem says ai fi to j is equal to aj j to I. So while determining the pair of u factors, first what you have to do is you find out the easiest shape factor, and then for the second body, to determine the shape factor of the second body, you apply the reciprocity theorem and then determine the second body. So either if you have two bodies, the equation changes as A1 F122 is equal to A2 F221. F122 means amount of energy or the fraction of energy leaving one and falling on body 2. F221 means fraction of energy leaving 2 and falling on body 1. Now in addition to the reciprocity relation, there is one more relation called summation rule to determine the shape factor. Suppose a body is kept inside a surrounding like this. A body, a small body, surrounded by, imagine several bodies. The amount of energy emitted by this body should fall on the surrounding bodies and must be absorbed or reflected. So the energy emitted by an inside body like this has to be received by the surrounding bodies. So which is nothing but the summation rule. So therefore the total sum of the U factors from surface I of an enclosure to all the surfaces of this enclosure including itself must be equal to unity. So sigma Fi to j, where j varies from 1 to n, is equal to 1, where n is the number of surfaces of an enclosure. Suppose n is 3, F1 to 1 plus F1 to 2 plus F1 to 3 equal to 1. If it is a flat surface, the radiant energy leaving from its own surface will not fall on it, as we have seen in the first case. So F1 to 1 becomes 0. Therefore, you will have F1 to 2 plus F1 to 3 equal to 1. So if the surface is flat, Fi to I, it cannot U itself, hence the U factor for such a flat surface will become 0. Now let us quickly look at few practical problems. Two concentric spheres are there, located one in another, one R1 solid sphere and R2 hollow sphere. Outer surface of this hollow sphere, let us assume reradiating, that means adiabatic thing, and let us assume these are both diffuse emitters and reflectors. Now determine the shape factor F1 to 1, F1 to 2 and F2 to 1. If you look at this, the total amount of energy emitted by the inner sphere has to go and received by fall on the sphere 2. So therefore F1 to 2 equal to 1, since all radiation leaving surface 1 strikes the surface 2. And F1 to 1 equal to 0 because no radiation leaving surface 1 can strike itself. It is a convex surface. So therefore the total energy leaving from F1 to 1 is 0, hence F1 to 2 should be equal to 1. Now once you know F1 to 2, you apply the rule, reciprocity rule, A1 F1 to 2 is equal to A2 F2 to 1. So F2 to 1 is equal to A1 by A2 into F1 to 2, where A1 is 4 pi R1 square, A2 is 4 pi R2 square, and this is R2 square into F1 to 2 is 1, therefore it becomes R1 by R2 whole square. Now if you look at the body 2, this body 2 emits energy. Some of the energy will go and fall on body 1, and some of the energy, you can see this arrow, will go and touch on itself. So the amount of energy emitted by body 2, portion of it can fall on itself. So therefore F2 to 1 plus F2 to 2 equal to 1. And F2 to 1 is R1 by R2 whole square. So therefore F2 to 2 is 1 minus R1 by R2 square. To determine the shape factor for some fixed geometries like perpendicular rectangulars with a common edge, either you can use the formula which we have discussed earlier, or you can also get a chart like this. And similarly for non-intersecting rectangulars, you can determine the shape factor by using this chart. So this chart solution is sometimes useful when the equations are so tedious. Standard data books and textbooks provide you these type of charts to determine the shape factor between different bodies like circular discs separated by a distance d, or circular plates, rectangular plates, and with the different orientations, etc. And it will be useful for solve many kind of problems. Now we have seen the reciprocity relation. A1 F1 to 2 is equal to A2 F2 to 1. The summation rule, that amount of energy emitted by a body 1 should go and fall on all the remaining bodies. So sigma F I to j, j is equal to 1 to n is equal to 1. Total energy should be equal to 100%. And now we will go for another simple rule to determine the shape factor, that is superposition rule. Now imagine there are 1, 2, 3 segments like this. The amount of energy released by 1 and falling on 2 and 3 is nothing but F1, 2, 2, 3 is nothing but F12 plus F12. You can split. So therefore, like this, F122 plus F123. So of U factor associated with a given geometry, when it is not available in standard tables and charts, it may not be available. So under such circumstances, it is desirable to express the given geometry as the sum of differences of some other geometries with known U factors. So the U factor from a surface I to a surface j, this is total, is equal to the sum of the U factors from surface I to the parts of surface j. Of course, you have to be very careful here. The reverse of this rule is not true. That is, the U factor from a surface j to a surface I is not equal to the sum of the U factors from the parts of surface j to surface I. So F1223, you can use the summation rule as F122 plus F123. Now multiply the entire equation with A1, you will get A1 F1223 is equal to A1 F122 plus A1 F123. And reciprocity relation says that the areas A2 plus A3 together, F2231 is equal to A2 F221 plus A3 F321. So from this, I can say F2231 equal to A2 F221 plus A3 F321 by A2 plus A3. So therefore, in such a case, we can say that the fraction of energy emitted by body 1 and falling on 2, 3 is equal to the sum of fraction of energy emitted by 1 and falling on 2 plus energy emitted by 1 and 3, summation put together. But anyhow, if you consider F2 to 3 to 1 from here to 1, it is not equal to F2 to 1 plus F3 to 1. So the U factor from a surface I to a surface j is equal to the sum of the U factors from surface I to the parts of surface j. And there is one more rule called symmetry rule. This symmetry rule says if you have a point source like this and there are symmetrical objects, the amount of energy falling on these two surfaces emitted by this will be equal. So Fi2j plus is equal to Fi2k. When two or more surfaces that possess symmetry about a third surface will have identical U factors from that surface. So Fi2j to Fi2k. So and by reciprocity relation, if I multiply with A1 Fi2j equal to Aj Fk2i, then because the areas are same, Fj2i is equal to Fk2i. We will check that symmetry rule with the help of a problem. determine the U factors from the base of the pyramid, that is from 1 to each of its 4 sides. What is F122? What is F123? What is F12? What is that 125? The base is a rectangle or a square, and all the side surfaces are isosceles triangles. So we assume again all faces are diffuse emitters and reflectors. And we take the base of the pyramid as 1 and 4 sides as 2, 3, 4, 5. The first thing we notice about this is symmetry. The 4 sides are symmetric about the base surface, either their angle, their Uing, or their configuration with respect to the base is same. So the amount of energy emitted by one should be shared equally among 2, 3, 4, 5. Therefore, we will have F122 is equal to F123 is equal to F124 is equal to F125. This is symmetry rule. And summation rule says F121 plus F122 plus F123 plus F124 plus F125 is equal to 1. Because plate 1 is a flat surface, F121 is equal to 0, and hence each of these 4 parameters, total sum is 1, and each of them are equal, and hence it is equal to 0.25. Note that each of the 4 sides of the pyramid receive 1/4 of the entire radiation, and also the presence of symmetry simplifies the determination of U factor or shape factor. Another problem. Determine the U factor from any one of side to any other side of infinitely long triangular duct, the cross section of which you have 3 surfaces here, A1, A2, A3. The duct is giving any surface that escapes to the ends of the duct is, therefore the infinitely long duct, which we have not shown, can be considered to be a 3 surface enclosures, L1 into infinity, L2 into infinity, L3 into infinity long. N is equal to 3. And by symmetry again you can see 1 to 2, F1 to 1, because all these are flat surfaces, F1 to 1 is 0, F2 to 2 is 0, F3 3 is 0. And F1 to 1 plus F1 to 2 plus F1 to 3 equal to 1 rule, F2 to 1 plus F2 to 2 plus F2 to 3 equal to 1, summation rule with reference to 2, and with reference to body 3 the summation rule can be written as F3 to 1 plus F3 to 2 plus F3 to 3 equal to 1. And already we have seen 1 to 1 equal to 2 to 2 equal to 3 3 equal to 0. And we know the equation, you multiply this with A1, A1 F122 plus A1 F123 equal to A1, A2 F221 plus A2 F223 equal to A2, and this equation is multiplied with A3. You remember, I think F33, F22, F11, diagonally these 3 values are 0 because they are flat. Now apply the reciprocity relation. A1 F122 is equal to A2 F221, A1 F123 is equal to A3 F321, A2 F223 is equal to A3 F322. So by substituting these values in this equation, by replacing the A1 which we know, and solving these three algebraic equations, you will get F122 is equal to A1 plus A2 minus A3 by 2A1, where A1 is L1 into infinity, so or L1 into X, that X both in numerator and denominator gets cancelled. You will get L1 plus L2 minus L3 by 2L1 as F122. Similarly for F223 and similarly for F123. In addition to these summation rule, symmetry rule, reciprocity theorem, etc., you have one more method called string method, cross string method. So therefore, in the cross string method, the surfaces of the geometry need not be flat. They can be convex, concave, or any irregular shape, but very easily you can apply this cross string method, and under a two-dimensional system you can determine the view factor. For example, body 1 is like this and body 2 is like this. Join the corners with the sides and diagonals as shown. You will get F I to j or 1 to 2 from 1 to 2 is equal to L5 plus L6, two diagonals, L3 plus L4, two parallel sides, divided by 2L1. So in the cross string method, the shape factor between two bodies can be found by using sigma of crossed strings minus sigma of uncrossed strings divided by two crossed strings, that is two strings on its surface. That means these are the diagonal strings L5 and L6. They are called crossed strings. And these are strings L3, L4, sum. So of strings minus sigma of uncrossed strings divided by the string on the surface I, when I want to determine F I to j, that is 2 times L1. Suppose I want to determine F2 to 1, then I have to take here 2 times L2, that's all. This is applicable even when the two surfaces are not flat, even when these two surfaces are not sharing a common edge, like in triangle. In such cases, the common edge can be treated as an imaginary string of 0 length. The method can also be applied to surfaces that are partially blocked by other surfaces by allowing the strings to bend around the blocking surfaces. Let us see an illustration to determine the shape factor between a plate AB and CD. Two infinitely long parallel plates. This is centimeter width, this 5 centimeter width, are located at a distance 6 centimeters apart. You are asked to determine the U factor from 1 to 2, F1 to 2, by using cross string method. So connect the strings. Now you can see here, these are the diagonals L5, L6. And L4, L3 are connected sides. And because I want from 1 to 2, I have to take A1. So sigma of crossed strings L5 plus L6 minus sigma of uncrossed, that is L3 plus L4 divided by 2L1. We know L1, L2, L3, L4, L5, L6. From the geometry we can calculate, and by substituting you will get the value F122 equal to 0.25. So simple, there is no complicated formula involved in this. Very easy and simple method. This method is called cross-string method, developed by H.C. Hotel in 1950s. Now the other second bit is, the geometry is infinitely long in the direction, and thus the two plates and the two openings are facing. Then apply the summation rule. One, two, three, 1, 2, 4, etc. L2, L3, L6, same so and so. So let us not much bother about determining from all other faces, etc. Now with this brief introduction on shape determination, now let us see a real heat exchange between two bodies. Let us use plate 1 and another plate 2, parallel, non-black bodies. The amount of energy emitted by body 1 is E1, and that E1 energy will come on body 2, and this body 2 will have an absorptivity, say alpha. So E1 alpha 1, and amount of energy reflected by this is E1 into rho 1. Sorry, rho 2, body 2. The second body will have, please follow carefully, the energy emitted by body 1 and falling on body 2 is E1. The second body has got a reflectivity of rho 2, therefore it reflects an energy equal to E1 into rho 2. But we know for a solid body, reflectivity plus absorptivity equal to 1, since transmittivity is 0. Therefore, the rho can be replaced with 1 minus alpha. So the amount of energy reflected from this plate 2 is E1 into 1 minus alpha 2. This E1 into 1 minus alpha 2 will come and fall on body 1, and again this body will have a reflectivity of rho 1. So therefore it reflects E1 into 1 minus alpha 2 into rho 1, and this rho 1 is equal to 1 minus alpha 1, and again E1 into 1 minus alpha 1 into 1 minus alpha 2 come and hits the body 2. The reflectivity of this body is again rho 2, so it reflects rho times the energy falling on it, that is E1 into 1 minus alpha 1 into 1 minus alpha 2 into rho 2, and that rho 2 is equal to 1 minus alpha 2, so it becomes 1 minus alpha 2 square. So the amount of energy reflected by the body 2 in the second collision is E1 into 1 minus alpha 1 into 1 minus alpha 2 square. Again the reflectivity of this is rho 1. So the amount of energy reflected by body 1 is E1 into 1 minus alpha 1 into 1 minus alpha 2 whole square into rho 1, which is nothing but 1 minus alpha 1. So it becomes 1 minus alpha 1 square into 1 minus alpha 2 whole square into E1. So like that, between bodies 1 and 2, multiple ray collisions are taking place. So therefore, we can say that the amount of energy reflected by one in the third reflection is E1 into alpha 1 whole square into 1 minus alpha 2 whole square. And I can say now the net heat from 1 is E1. You can see, look here, E1 and the amount reflected back, E1 into 1 minus alpha 2 into E alpha 1 plus E1 into 1 minus alpha 2 square into 1 minus alpha 1 into 1 alpha 1, etc. Let us assume P equal to 1 minus alpha 1 into 1 minus alpha. So Q net is equal to E1 minus E1 into, take out 1 minus alpha 2 alpha 1 common, you have 1 plus P square and so on. This 1 minus P plus P square is the binomial expansion of 1 minus P to the power minus 1. So I can write Q is equal to E1 minus E1 alpha 1 into 1 minus alpha 2 by 1 minus P. 1 minus alpha 1 into 1 minus alpha 2. So on simplification, you will get Q1 is equal to E1 into epsilon 1 by epsilon 1 on 2 minus epsilon 1 epsilon 2, because the absorptivity is equal to emissivity. And similarly, you can write Q2 equal to E2 into E1 by E1 plus E2 minus E1 E2. And Q122 at heat exchange is E1 epsilon 1 minus E1 E2 epsilon 1 by epsilon 1 plus epsilon 2 minus E1 epsilon 1 into epsilon 2. Emissivity of body 1 is epsilon 1 sigma T1 to the power 4, and emissivity of body 2 is 2 sigma T to the power 4. So therefore, you can write now Q122 equal to epsilon 1 into epsilon 2 common, and this denominator is common. You will have common, and T1 power 4 minus T2 to power 4. So Q122 is equal to sigma T1 to the power 4 minus 2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This can also be written as sigma T1 power minus 4 into T2 power 4 into F122, where F122 is equal to 1 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1, and is known as interchange factor. So that much amount of difficulty is there to determine radiation heat exchange between two bodies, because each time when the ray is falling on a body, a fraction of it is absorbed and the fraction of reflected. Again here a fraction of it is absorbed and fraction is reflected. So due to multiple reflections, ultimately what is the amount of energy leaving the surface and what is the amount of energy contained by the surface, you have to go on writing series of expressions like this and determine. It's a very tedious process. So therefore, we will identify a simple method to determine the heat exchange between two surfaces using electrical analogy. For that purpose, we need to arrive two important resistance. One is surface resistance, other one is shape resistance. Let us see what is surface resistance and what is shape resistance. You imagine there is a surface. G amount of radiation is incident on it. When the surface has got reflectivity rho, rho part of it gets reflected. By virtue of its temperature, this surface also continuously emit energy, and that amount of energy emitted by it is epsilon times that of amount of energy emitted if it is a black. Because it is not a black body, the energy emitted is epsilon into EB. Now, the total amount of energy leaving this surface is rho g, that is the reflected part, and epsilon into EB, that is emitted part. This put together is called radiosity. So radiosity is the total radiant energy leaving a surface per unit time and per unit area. Epsilon into EB plus rho into G is equal to J. We know for a solid body transparency is 0. Therefore, alpha plus rho is equal to 1, rho is equal to 1 minus alpha, and alpha is equal to m for a gray body, so rho can be written as 1 minus epsilon. So that leads to the radiosity J is equal to epsilon into EB plus 1 minus epsilon into G, irradiation amount of radiant energy. So J is equal to epsilon into EB plus 1 minus epsilon into G, where EB is sigma T to the power 4, the emissive power of a black body, and G is the irradiation, that is the radiation energy incident on surface per unit time per unit area. If you assume that body is a black body, epsilon I becomes 1. So therefore, this part becomes 0 and this is 1. So you will get J equal to E. So the radiosity of a black body is equal to its emissive power. Very simple expectation, because a black body does not reflect any radiation, and thus the total radiation coming from a black body is to emission only. See, for example, if this is a black body, there won't be any reflection, rho g. It becomes 0. So incident G is equal to the radiosity J equal to EV. That is what is said. Under such circumstances, what is the net radiation heat transfer to or from a surface? Simple. Net heat transfer is radiation leaving the entire surface and radiation incident on the entire surface. J minus G, where J is the radiosity, G is the irradiation, radiation intensity that is falling on it. And we know J is equal to epsilon EB plus 1 minus epsilon into GI, and hence GI can be written as JI minus Ji minus epsilon I into EBI by 1 minus epsilon I. Now I can say that heat transfer by means of radiation Q is AI into Ji minus this part, Ji minus Gi. Ji is like this, Ji minus Zi is Ji minus epsilon I to EBI by 1 minus epsilon I. So this is equal to AI epsilon I by 1 minus epsilon I into EBI minus Ji. This EBI minus Ji. So this is simplified as QI is equal to EBI minus Ji by 1 minus epsilon I by AI epsilon I. EBI minus Ji, emissive power of a black body minus radiosity. Strictly speaking, it should be the radiant energy leaving the surface, net radiant energy, but the term which is reflected in the denominator is reducing it. Hence, this term is called resistance. And that resistance is because of emissive nature of this surface, because its emissivity is not equal to 1. Therefore, the surface characteristics of a body decides how much amount of radiant net energy leaving it if it is not a black body, and this contributes to that, hence known as surface resistance. So if you have a surface like this, the net radiant energy leaving EBI minus JI divided by this resistance 1 minus EI by EIAI. QI is equal to EBI minus JI by RI, where RI is 1 minus epsilon I by epsilon I AI. If it is a black body, it becomes 1 minus 1, 0, where Ri is called surface resistance. EBI minus JI is called potential difference. QI is the net rate of radiation heat transfer, which corresponds to current in the electrical analogy. So therefore, net radiant heat transfer from a surface to the environment can be determined by using the formula QI is equal to AI into J minus GI, and it can also be written as QI is equal to EBI minus JI by RI. This direction of net radiation depends on the magnitude of EBI and JI. If EBI is greater than JI, it is from the surface. If JI is greater than EBI, it is to the surface, where JI represents radiosity and EBI represents emissive power of a black body. If you get QI negative, it indicates that heat transfer is to the surface. So when you are dealing with a negative value, you have to subtract it. The surface resistance to radiation for a black body is 0, because EI is equal to 1, and then JI will be equal to EBI. That is what we have seen. No resistance, whatever amount is emitted is nothing but the radiosity. And the net rate of radiation heat transfer in this case determined directly as AI into JI minus GI. Re-radiating surface. This is another concept in the radiation heat exchange. Most of the surfaces in the practical heat transfer are treated as adiabatic in nature. That means their rare back surfaces are insulated, and net heat transfer through the backside surface is termed as 0. When the convection effects on the front side of such surface is negligible, the surface must lose as much radiation energy as it gains, and thus QI, net radiant, is equal to 0. In such cases, the surface is said to re-radiate all the radiation energy it receives and is called re-radiating surface. QI, as we have seen, EBI minus JDI by RI, and when it is re-radiating surface, EBI is equal to JI. Therefore, the temperature of a re-radiating surface under steady conditions can easily be determined from the above once its radiosity is known. The temperature of a re-radiating surface is independent of its emissivity. Since there is no heat transfer through it, the surface resistance of a re-radiating surface is always neglected. This is like the fact that there is no need to consider resistance in electrical network if no current is flowing through it. Now we will introduce the second resistance in the heat transfer by radiation, that is surface resistance. A surface I is there which some amount of energy emits, overcoming its surface resistance, Ji is leaving. Another surface J is there, overcoming its surface resistance, some J, suffix J is leaving. But as we have seen, not the total amount of energy leaving one surface will come and fall on the other surface. Only a fraction of it will be received by the second body. That leads to another resistance called shape resistance. Net radiation heat transfer from I to J is given by AI Ji F to J minus AJ JJ Fj to I. According to reciprocity relation, AI to J equal to AJ Fj to I. So you can write Qi to J as AI to J into Ji minus Jj, which is equal to Ji minus Jj by 1 by AI to J. This 1 by AI to J in the denominator reduces the net radiant heat energy between Ji and Ji and is known as a resistance. And this resistance is called shape resistance. So Qij is equal to Ji minus Ji by Rij. This Rij, if you look at it, it is 1 by AIF I to J or 1 by AJ F J to I. This Ri to J is called space resistance or shape resistance, and Ji minus Jj is called potential difference. Qij is positive to represent that heat from surface I to J. Negative value indicates the opposite direction. So now if you combine both the surface and space resistances, the layout looks like this. Qi is equal to sigma Ebi minus Ji by Ri, sigma J equal to 1 to N Ji minus Jj by Rij, where Ri is 1 minus epsilon I by Ai, and Ri to J is 1 by A1 F 1 to 2 or AIF I to J. Net radiation flow from a surface through its surface distance is equal to sum of the radiation flows from that surface to all other surfaces, including itself, through the corresponding space resistances. Now we will see the network method or electrical network analogy. What we have identified now is, in case of radiation, two types of resistances exist. One is surface resistance and other one is shape resistance or space resistance. Surface resistance is given by the formula 1 minus epsilon I by epsilon I Ai epsilon I, and shape resistance is given by the formula 1 by AIF I to J. So draw a surface resistance associated with each surface and connect them with space resistance. Then solve the problem, treating it as electrical network problem. When more than 3 or 4 surfaces are involved, this electrical analogy or network method becomes complex and we cannot solve it easily. Let us take case by case. radiation heat transfer in two surface enclosures. Say Q1, Q2 we want to find is equal to Q1 minus Q2. So EB1, EB2 from 1 to 2, first from surface 1 to 2 you have shape resistance of surface 1. And then the energy has to flow and some of it only will fall on 2. So you have in between shape resistance. Because of the emissive nature of the second surface, its emissivity is not equal to 1. Only a fraction of it will be absorbed. Hence, this also offers some amount of surface resistance called R2. So, between 1 and 2, 3 resistances exist. One after the surface resistance 1 minus E1 by E1 A1, shape resistance 1 by A1 F122, and third again surface resistance 1 minus E2 by E2 A2. Now I can say Q122 is equal to EB1 minus EB2 by R total, R1 plus R2 plus R3, 1 minus E1 by A1 E1 plus 1 by A1 F122 plus 1 minus E2 by A2 E2. So this is the general formula for radiation heat exchange between any two surfaces having emissivities and separated by a distance. Suppose you have a small object in a cavity, A2 is very small, A1 is very large, it becomes approximately 0, and from this 1 to 2 is almost equal to 1. You substitute here, A1 by A2 is 0 and F122 is 1. So you will get Q122 is equal to, this term vanishes because A2 is infinity and F122 is 1. So 1 by A1 E1 plus, minus 1 by A1 plus 1 by A1 cancels. You have only 1 by A1 in the denominator. It goes up. So Q122 is A1 epsilon 1 sigma T1 power 4 minus T2 power 4. Now let us take two infinite large parallel plates. So again 3 resistances, infinitely large, approximately A1 equal to A2. And 1 to 2, because those two plates are running parallel to one another, F122 is 1. So A1 is equal to A2 and F122 is 1. By substituting you will get Q122 is equal to sigma T1 to the power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. If you have two infinitely long concentric cylinders like this, R1 is the radius of the inner solid cylinder, R2 is the radius of the hollow outside cylinder. F122 is equal to 1 because the amount of energy emitted by the solid cylinder can go and fall only on the outer cylinder. And we know A1 by A2 is 2 by 2 pi R2L becomes R1 by R2, and this formula Q122 again reduces to A1 sigma T1 to power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 minus epsilon 2 by epsilon 2 E2 into R1 by R2. Concentric spheres are there, same analysis, you will get another expression like this. So my advice is not to by heart all these formulae. You remember only the two resistances that are encountered in radiation heat transfer. One is surface resistance and one is shape resistance. Draw the resistance circuit algebra like this between 1 and 2. Identify if black bodies are there, epsilon 1 becomes 1, and if the areas are infinity or one is small and one is large, and determine shape factors of F122, you substitute in these resistances, you will get Q122. So that is what you have to do before going to the solving problems. Take a simple problem like this. Determine the net radiation heat transfer between two large parallel plates maintained at uniform temperatures as shown here. See, both plates are given some emissivities, E1 0.2, E2 0.7. So they are not black bodies. So they offer surface resistance. Each one offers surface resistance. And not the total. Two large parallel plates. So therefore, the amount of energy leaving one has to fall on body 2. So in between 1 and 2, there exists a shape resistance. So altogether, 3 resistances. First one is 1 minus epsilon 1 by epsilon 1 A1. The second one is 1 by A1 F122. And the third one is 1 minus E2 by E2 A2. F122 equal to 1 because they are two large parallel plates. A1 equal to A2, both are very large parallel plates, say A. So take out A common, you will get the expression 1 by epsilon 1 plus 1 by epsilon 2 minus 1 for total resistance. So Q is equal to sigma T1 to the power 4 minus T2 power 4 by 1 by E1 plus 1 by E2 minus 1. Substituting those values, you will get 3625 watts per meter square. 2.5 centimeter diameter small pipe whose surface is maintained at 1000 Kelvin having emissivity 0.1 is enclosed inside a large pipe of diameter 7.5 maintained at 350. Determine the heat loss from inner pipe to outer pipe per meter length if the emissivity of outer pipe is 0.3. Let us assume the outer surface is insulated. Again, here also you can see 3 resistances are there. One is surface of inner pipe, shape resistance between inner and outer pipe, and surface resistance of outer pipe. 1 minus E1 by E1 A1, 1 by A1 F122, 1 minus E2 by E2 A2. And F122, the amount of energy released by 1 can go and fall only on body 2, so F122 is 1. And R total expression you can write the sum of these 3, which can be simplified as 1 by epsilon 1 A1 plus 1 by epsilon 2 A2 minus 1 by A2. Now A1 is equal to pi R1L and A2 is equal to pi R2L, and R total you can determine. Now we know A1, A2, F122, etc. And the Q equal to sigma T1 to the power 4 minus T2 power 4 by R total, which is equal to 5.67 in 10 power minus 8, 1000 to the power 4 minus 352 power 4 by 137.2, which is 407 watt per meter length. See, in all these cases, whenever there are two bodies, simple network, one surface resistance, between the two bodies a shape resistance, and third one a surface resistance. Suppose the second body is given as black body, what will happen? E2 you will put 1. So it becomes 0. You will have only 2 resistances. If the first one is also a black body, this one also becomes 0. You will get simple equation Q equal to sigma T1 power 4 minus T2 power 4 by 1 by A1 F12. So you take the data, draw the circuit, identify epsilon 1 F122 A1 A2 E2 values, substitute, use the formula Q equal to EB1 minus EB2 by R total. You will get this answer. A small gray body 1 is kept in a large enclosure. So the amount of energy emitted by 1 will go and fall on body 2. Therefore F122 is 1. Again 3 resistances like this. Because A2 is a large enclosure, it is equal to infinity. So A2 being infinity, it cancels. You will get 1 by epsilon 1 A1. Now Q equal to sigma T1 power 4 minus T2 power 4 by 1 by epsilon 1 A1, which is nothing but epsilon 1 A1 sigma T1 power 4 minus T2 power 4 equal to 6.2 watts. I hope by this time now you understood how to apply the electrical analogy and how to consider the different resistances like shape resistance and surface resistance when two bodies are exchanging heat with one another. Now let us take like two rectangular plates whose walls are black. These two are black bodies. So the surface resistance of A1, for example, 1 minus E1 by E1 A1, E1 is 1, 1 minus 1, 0 by something, 0, no resistance. Similarly, the surface resistance of A2 is 0. So what is left out? Only shape resistance. So J1, J2, 1 by A1, F1, 2. So now Q equal to sigma T1 to the power 4 minus T2 power 4 by 1 by A1 F12. What is F122? Shape factor. The amount of energy leaving 1 and falling on body 2. That we have to find. So you can use the graph presented in the earlier slides, or you can also use the formula given in the earlier slides to determine the shape factor between 1 to 2, and from the graph we obtain F A1 to A2 as 0.2. Using it, get the R total, and Q is equal to 17.01 kilowatts. That is about the radiation heat exchange between two surfaces. If you have three enclosures, 1, 2, 3, you imagine like this, 1, 2, 3. Each surface is having its own surface resistance, see R1, R2, R3. Between 1 and 2, you have shape resistance. Between 1 and 3, you have shape resistance. Between 2 and 3, you have shape resistance. So you have to formulate EV1 minus J1 by R1, J2 minus J1 by R12, J3 minus J1 by R13, this one, equal to 0. You understand? So like that, this network you have to solve, and you will get three equations. From these three equations you have to determine the values like EV1, EV2, EV3, etc. The algebraic sum of the currents at each node must be equal to 0. That is the principle in writing these equations. But anyhow, when three gray bodies are there, solution of this involves solution of simultaneous algebraic equations. More the number of surfaces, more algebraic equations you have to solve simultaneously, and that requires some kind of package. A furnace is shaped like a long equilateral triangular duct, and width is 1 meter each side. Base has an emissivity 0.7, and this side is black and this is insulated. So first let us take surface 1. You have surface resistance R1. Surface 2, black body, so there is no surface resistance. Surface 3, insulated, no heat transfer. Q3 is 0. And between 1 and 2 you have a shape resistance. Between 2 and 3 you have a shape resistance. Between 1 and 3 you have a shape resistance. Now the network analogy says the total heat transfer Q1 is equal to EB1 minus EB2 by R1 plus 1 by R122, that is this one, 1 by R122 plus these two are in series, 1 by R13 plus R23 whole to the power minus 1. So that is R1, 1 minus epsilon 1 by A1 epsilon 1 R12 1 by A1 F122 1 by R12 A1 F122 plus 1 by R123 A1 F123 A2 F223. And if you look at this F122 F123 equilateral triangle, so therefore the shape factor from F22 is 0.5, F123 is 0.5, 322 is 0.5, 321 is 0.5, 221 is 0.5, 223 is 0.5. Because all the surfaces are flat, they cannot U themselves. So F121 is 0, F222 is 0, F33 is 0. Hence, you will get the shape factors 0.5 because of the symmetry. By substituting the values, you will get minus 28 kilowatts. Therefore, 28 kilowatts must be supplied to the heated surface per unit length of the duct to maintain steady operations in the furnace. Very important application in the radiation heat transfer is with reference to radiation shields. Generally used in cryogenic systems and space applications, nuclear reactors, to minimize the radiation losses. These radiation shields also used in temperature measurement of fluids and gases to minimize the error because of radiation from the probes. The role of the shield is to reduce the rate of radiation heat transfer by placing additional resistance in the path of radiation heat flow. Radiation shields are materials having high reflectivity, that means low emissivity, and such high reflective thin plates or shells are called radiation shields. Suppose you have a plate 1 like this, 2 like this. The radiation heat transfer from 1 to 2 can be reduced by keeping in between a shield with an emissivity E3. Now between 1 and 2, 1 and 3, you have first surface resistance, then shape resistance, and then the left side surface resistance. And here right side surface resistance, shape resistance, and again left side shape resistance. So total resistance increases. 2 more resistances and 1 shape resistance are added to it. So altogether the total rate of heat transfer reduces. So Q122 without shield is sigma A T1 power 4 minus T power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Whereas with the shield is, you can see there are 6 terms and it reduces to 1 by epsilon 1 plus 1 by epsilon 2 minus 1 plus 1 by epsilon 3 comma 1 plus 1 by epsilon 3 comma, that is third is the shield phase 1 and phase 2 minus 1. So Q with no shield is 1 term. Q with 1 shield is you have 2 terms. Suppose you have Q with 2 shields, you have 3 terms, and if you have 3 shields, you have 4 terms like that. So for n radiation shields, you will have totally n plus 1 terms. So Q with n shields is equal to 1 by n plus 1 of Q with no shields. This is not 1 shield, actually it is Q with n shields. So 1 shield reduces the rate of heat transfer to 1/2, 2 shields reduce it to 1/3, and n shield reduces to 1 by n plus 1 times. However, in practice, the radiation shield will have much lower emissivity than the plates, and hence the reduction is more significant. So with n shields it is 1 by n plus 1 times without a shield. Now if you want to determine the temperature of the shield in between, we will just do it by equating the energy flow. Q122 is equal to Q123 is equal to Q223 under steady state condition. By equating these two heat transfers, you will get the value of T3. Epsilon 3 represents the MCUT of shield. Epsilon 1 and epsilon 2 are MCUTs of the plates. The same way you can treat the heat transfer between concentric spheres and cylinders also. A thin aluminum sheet with an MCUT of 0.05 on both sides is placed between two very large parallel plates. One is at 800 degrees centigrade, that is 1073 Kelvin. Other one is at 500 degrees centigrade, that is 1073 Kelvins. Having MCUTs epsilon 1, epsilon 2, 0.3, 0.4. Generally, the radiation shields are of active nature. Rho is very high. Rho is equal to 1 minus alpha, or alpha is equal to 1 minus rho. Because rho is very high, highly reflective, alpha, absorptivity, is very low. For a gray body, absorptivity is equal to MCUT, hence a radiation shield will have low MCUT. Let us consider 0.05. So when there is no shield, the formula is sigma A T1 power 4 minus T2 power 4 by E1 plus 1 by E2 minus 1. You will get 11.36 kilowatts per meter square. If shield is kept in between like this, now resistances add. Between 1 and 3 you have 1 by S 1 by epsilon 3 of first side minus 1 plus epsilon 3 of second side plus 1 by epsilon 2 minus 1. So by substituting Q122 you will get 1.25 kilowatts per meter square. So almost the radiation heat transfer reduces in end, or it becomes 1/10 by keeping only one radiation shield. And the shield temperature can be found by equating, as we did, Q is also equal to sigma T1 to the power 4 minus T3 power 4 by 1 by epsilon 1 plus 1 by epsilon 3, that is on the left hand side 1 3 minus 1. So you will get T3 equal to 955.4 Kelvin, or roughly around 727 degrees centigrade. Another important application of this radiation shield is to reduce the error in the temperature measurement. Suppose a fluid is flowing through a duct. When we immerse a thermometer to read its temperature, the thermometric bulb will not only convect heat to the surroundings, it absorbs heat from the gases by means of convection. Under high temperature, it starts losing heat to the environment by means of radiation. This radiation heat transfer, when it is more, the probe reads a low temperature than the actual, resulting in high error in the measurement. So what is that? Let us see. Q convection to the sensor to Q radiation from the sensor. That is H into fluid temperature, TF minus thermometer temperature is equal to epsilon sigma thermometer temperature minus wall temperatures, TW to the power 4. A small body in a large enclosure. So from that you can determine the fluid temperature TF is equal to thermometer temperature plus this term. This term is additional term which is called radiation effect correction term. Radiation correct term is most significant when the convective transfer coefficient is small and the emissivity of the sensor is very high. You can see here. When epsilon is high, more and more correction. When H is less, this term becomes more and more. So to avoid that, the sensor should be coated with a material of high reflectivity to reduce the radiation heat transfer. Or you can place the radiation shield without interfering the fluid flow, reduces the radiation. That is, you have to keep two parallel lines like this, two parallel shields, so that the flow will not get disturbed, but that shield which is kept between thermometer and the wall will be at an intermediate temperature TW and TDH and reduces the effect of radiation. Therefore, the error is minimized. So, sensors of temperature measurement device used outdoors must be protected from direct sunlight, since the radiation effect in that causes an error in the measurement. Let us check a problem. 650 Kelvin is the thermometer temperature showing. Wall temperature is 400. Emissivity of the thermometer bulb is 0.6 Kelvin. Heat transfer coefficient is given 80 watts per meter square Kelvin, and the emissivity of the thermocouple is 0.6. Now what is the actual air temperature? Is it the measured temperature or not? See, the formula let us apply. The fluid temperature is thermometer temperature plus epsilon into sigma TTH to the power 4 minus TW to the power 4 by convective transfer coefficient H. You will get the answer 715 Kelvin. The thermometer shows only 650 Kelvin, but the fluid temperature is 715 Kelvin. So if you want to reduce this type of errors, the best thing is keep radiation shields. Two radiation shields we will keep parallel to the flow and perpendicular to the paper, such that the flow is not obstructed, but because of these radiation shields, the radiation heat loss from this bulb is restricted. Thereby, the error in the temperature measurement will become low. Now let us quickly look at the points what we have seen today. Shape factor is defined as the fraction of radiant energy from one surface of a body received by the another body and is denoted as F122. Shape factor 122. Fraction of energy leaving one and falling on body 2. Shape factor, configuration factor, U factor, angle factor. You can call it by any name. Shape factor between two black bodies can be determined by using the formula 1 by pi A1 double integral over areas A1 A2 cos theta 1 cos theta 2 by S square dA1 D2, where S is the distance between the bodies A1 and A2. The reciprocal theorem states that AM F M to N is equal to AN F N to M. The summation rule says that sigma K equal to 1 to N F of I to K is equal to 1. If the surface is flat, F I to I or 1 to 1 or 2 to 2 is equal to 0. The rule of superposition helps in finding the shape factor of complex geometries. And the symmetry rule states when two or more surfaces possess symmetry about a third surface, they will have identical U factor from the surface. The radiosity is defined as the total or the sum of a reflected portion of energy from a surface plus emitting power. Surface resistance for it is 1 minus epsilon by epsilon into A. Shape resistance is 1 by A1 F122. Electrical analogy provides a simple technique to solve radiation problems using surface resistance and shape resistance. Radiation shields are of high reflecting surfaces used to minimize radiation heat loss. Error in temperature measurement due to radiation loss from a thermocouple can be minimized by providing radiation shields. Most of the surfaces exhibit combined convection and radiation heat transfer. However, radiation is dominant only at higher temperatures. Otherwise, it can be negligible. That's all about the radiation heat exchange. Let us have a quick look at the concept, questions and answers. What does the U factor represent? When is the U factor from a surface to itself not zero? The U factor represents the fraction of radiation leaving surface I that strikes the surface J directly. U factor to itself is a non-zero for concave surfaces because some of the energy leaving surface can go and fall on it. How can you determine the U factor F when the U factor F2 to 1 and the surface areas are available? Using reciprocal theorem, A1 F122 is equal to A2 F221, you will get F122. What are the summation rule and superposition rule for U factor? The summation rule says that when there are n number of surfaces, the sum of the U factors from surface I of an enclosure to all the surfaces of enclosure, including itself, must be equal to 1 unity. The superposition rule states that U factor from a surface I to a surface J is equal to sum of the U factors from surface I to the parts of the surface, that is F12 2, 3 is equal to F122 plus F123. How does radiosity for a surface differ from emitted energy, and for what kind of surfaces are these two quantities equal? Radiosity is the total energy leaving surface, which includes emitted energy as well as reflected energy. Radiosity and emitted energy are equal for black bodies since black body does not reflect any radiation. What are the two methods used in radiation analysis? How do these two methods differ? One is network method and another one is matrix method. N unknown radiosities for n surface enclosures. That way, network method involves drawing a surface distance associated with each surface and electrical network problem solution, etc. Please go through this. Already we have seen this. What is a reradiating surface? What simplification does a reradiate for in the radiation analysis? Some surfaces encountered in numerous practical heat transfer applications are modeled as being adiabatic, as the backsides of these surfaces are insulated and net heat transfer through these surfaces is zero. Those are called re-radiating surface. And the convection effects on the front side of such surface is negligible. Under steady state conditions, the surface must lose as much radiation energy as it receives. Such a surface is called re-radiating surface. In radiation analysis, the surface resistance of a re-radiating surface is taken to be zero since there is no heat transfer through it. What is a radiation shield and why is it used? Radiation heat transfer can be reduced by inserting a thin, high reflective, that is low emissivity, sheet of material like silver foils, etc., gold foils having high shiny nature. Such highly reflective tins are known as radiation shields. Multi-layer radiation shields constructed of about 20 shields per centimeter thickness separated by evacuated space are commonly used in cryogenic and space applications to minimize heat transfer. Radiation shields are also used temperature measurements of fluids to reduce the error caused by the radiation effect. What is the radiation effect? How does it influence the temperature measurement? The influence of radiation on heat transfer or temperature of a surface is called radiation effect. The radiation exchange between the sensor and the surroundings may cause the thermometer to indicate a different reading for the medium temperature. To minimize the radiation effect, the sensor should be coated with a material of high reflectivity, low emitting nature, or you can keep shields to minimize the error. That's all about this chapter on heat exchange between radiation heat exchange between two surfaces. With this chapter, we are concluding the sessions on heat transfer. Series of lessons we have seen with regard to the subject heat transfer, where we have not touched the multi-dimensional heat transfer problems, and we have not considered various unsteady state condition, state conduction, and we have not considered any problems with heat radiation between more than two bodies. So with these limitations, the heat transfer course till today, what we have seen, covers almost the syllabi of various Indian and foreign universities with respect to undergraduate coverage. So I request the students not to limit to this discussion, taking this as only a basis for understanding the fundamentals and developing the concept. They have to more vigorously do the exercise problems given in the standard textbooks like narrated here, a heat and mass transfer by Sengel or by Frank Reith, Incropera and Dewitt, etc. Thereby, through practice only they can learn the subject and they can understand the concepts behind it. They can grasp the practical aspects of heat transfer in day-to-day life as well as in several engineering applications. I sincerely thank the Koner-Lashmaya University management for giving me this opportunity to deliver the series of lectures on heat transfer, and my heartfelt thanks to Professor Vedula, the coordinator for Indo-US Consortium for Engineering Education, and I am also thankful to Mr. Sridhar and his team for their unstinted efforts in recording these events, even though there are many hiccups with reference to internet connectivity problems, and many others who have directly or indirectly helped me in delivering these lectures. Thank you one and all.